Hi, my name is Ken Lasseson. I'm a data scientist and also a software development engineer. I wrote a microbiome analysis site for people to look at their microbiome analysis coming back through a 16S lab process. Today, I want to talk about the importance of entering symptoms. They're important not solely for citizen scientists like I am and researchers, but they are very important in order to better get the right suggestions for you. And the reason is there's tremendous variations of people in terms of their microbiome profile. So let's first take a look at entering suggestions, and then I'll talk about what we have discovered. So go to your sample and then click Enter Symptoms. These are the symptoms when the sample was taken. For example, go in and take a look at your age. Okay, mark there. Take a look at there. Notice that the things expand and contract, so you're not hit with a massive page of things. You just simply take a look at everything. Go through and see which ones are representative of you. And okay, gone through that one. Let's go through the next one. Anything there? Shortness of breath occasionally. Blood type. I think I'm O positive. Mark that. Cold, morbid mouth. I do have a tendency towards dry mouth. Comorbid conditions, do have inflammatory bowel, EMF sensitivity, high anxiety, mood swings, yes, restless legs, yes, and we go on, and once we're finished, we simply click update. That's it. We are now have entered our symptoms, and now we can start reaping the rewards. And the rewards you can see by flipping over to Symptom Explorer, and we can go in and take a look at symptoms to significant bacteria table. And what we have is a table showing all of the conditions where there's a very strong relationship between a particular bacteria or groups of bacteria and a particular symptoms. Now, at this point of time, I should point out that the traditional approach has been for people to look at a defined medical condition and try finding the bacteria associated with it. Seems absolutely logical. However, I personally have had to deal with chronic fatigue syndrome, which has something like 120 to 140 different symptoms. And technically, at one time, all you had to have is 4 of those 120 symptoms to get a diagnosis, as nothing else can be wrong. So when I clued in to the possibility that symptoms are caused by bacteria, not by whatever the condition is, then we want to take a look at the bacteria and the symptoms in comparison, not the bacteria and the condition. And the result is that suddenly we have a whole bunch of relationships popping out very strongly, and it's a very long list. These are all things which are very distinctive. Now, on the right side, you will see the evidence for it. For example, this one, bloating, just one particular species. What we have is we have some of them, but very small numbers of them being a pattern, which is very strong. Let's go over and explain how we get these numbers and why we want to do things with them. What we do is a technique which is quartering symptoms. So how many bacteria do we have? Let's take a look at one particular type of bacteria. If you look at everybody who has contributed samples and see how many you have of any bacteria, for example, Staphylococcus gordoni here, we go through and we can plot out the thing. And you notice that it's not a nice bell curve. it is a very skewed, that is very shifted curve. And instead of trying to work from the average value, which would be probably somewhere around here, we are going to divide all these numbers into quartiles, into quarters. So 1/4 is here, 1/4 is here, 1/4 is here. And if we do that, we find that the first quartile is values from 4 to 41, second one is 21 to 95, third one is 98 to 207, etc. Now, we notice that the key thing is the number of people in each quartile is the same. In this case, about 20 people. The values are not the same. The range is very different between them. And that is where the elegance of data science comes in, is that we don't just look at the ranges. What we do is we look at the size of the population in each group. Now, when we apply this to symptoms, for example, exertional malaise, we go and we discover something. The table is shown below, but I will also take a look at the table. If you click on the link, you go to the table, and the table is shown here. And you notice we have 3 different bacteria, which all pops out as being significant. This one here, we see that the high quartile is where all of the values have shifted to. Here to the low one, here to the low one. So in other words, we have 3 major shifts. Instead of being evenly distributed for people with the symptoms, they all are high for one, and almost all of them are low for the other 2. So what we basically can think of it is, think that we have a 4-sided die. If we toss it 400 times, we expect 100 times for each one of the sides to occur, somewhere around 100, 95, 108, etc. But if we have 10, 10, 190, and 160 being the numbers showing up, you're not going to believe you were given a fair die. Somebody has given you a biased die. And we are working the same logic here. The bacteria is associated with the condition, and we see the shift. Over here on the right side, we have the p-value, the probability value, and we see the probability of this happening is 0.0004, which means 4 chances out of 10,000 that this would happen by random chance. And we only have, in this case, we only have perhaps 200-300 people, so the odds are very unlikely it would be happening by random chance. That for this one, let's go in, and I looked at the database behind, and the actual ranges we are using are shown. So we have a range of 200, almost a range of 300, then we jump up to almost a range of 700, and then whatever values goes up to. If we look at the chart, we see the chart below, and we see the value goes up to almost 20,000. And the average value is 1,311. So the average value is way up here. And if you're trying to detect by using averages, you're going to have a rough time. That's why we use the quantile method. We divide it into 4 and see whether or not we have a biased dice or a biased bacteria. And so bottom line is that is how we determine if a bacteria is significant. Okay, returning to the chart, you see there's a button there to make, which simply means it's hyperlinked to the actual information about the bacteria. So if you click that, you go over to our library, which gives you all sorts of technical information. But what we also see is all of the different types of symptoms which are strongly associated with it. So let's take a look at a couple of them to see what we mean. For example, let's try multiple chemical sensitivity. If you click on that one, we go down and we see that this bacteria is shifted to the left in a bit of an unusual manner for those who have multiple chemical sensitivity. It may mean that there are 2 different subsets within that which we haven't been able to differentiate. But we now see we have that particular bacteria is associated with that one. But now let's go over and look at tender sore lymph nodes and go down and look at this one. Again, it shows up, again, low numbers. And we can again return by simply clicking through. Aching behind the eyes, we go down, and in this case we have other bacteria are associated. So we have 3 types of bacteria which are very low, and when those 3 of them are low together, the probability of getting aching of the eyes or behind the eyes goes up. And let's go back to one more. Oh, female. Wow, let's take a look at female. What's the chances? And what we have here is we find, again, we have this odd double bias. We have things shifted, but from the top to the middle and from the bottom to the very low. So there's a double shift happening here, but there's also an increase of a particular species. It's much higher when it comes to females. And that's basically the fundamentals of what we are doing. So how does this tie into custom suggestions? Here's a custom suggestion page, and I only want to go through a little bit of it. We have bacteria selection choices here, and this one basically will show you which bacteria are going to be used for making suggestions from. In this case, although I have entered symptoms, there's absolutely no matches there. I'll show you an example in a moment where there are matches. And then below that, we have the bacteria identified by a method called the box plot, which identifies the 50 bacteria which are abnormally outside the expected range. But then we go further down and we see ones which are outside of the average range, and we see that it jumps up to 131 different bacteria. Now the question is, it's unlikely that all 131 are really significant. Lots of those are randomness or they have no impact. So the result is we really want to keep to a lower number. 50 is much better to try to work from suggestion from. But if we had some with symptoms, then we are really lucky because then we can get very explicit examples. Here is another example of somebody who has entered symptoms, and in this case, she has really hit the jackpot. We have 27 bacteria associated with her symptoms, which is a nice ratio. Now, the weight here indicates basically, is it too high or is it too low? So positive is too many and negative is too few. If you go down to outliers, we have 59. So we basically have the number of bacteria we're going to try figuring out solutions for by 50%. And if you go further down, we see 132. So by using the symptoms, and if you're lucky, you're getting a symptom to bacteria match, you suddenly have a good idea of which bacteria is the source of your symptoms, which means probably the source of your condition. Okay, so that's the importance of doing symptoms. Get those symptoms in. It gives everybody information to do analysis from, but more importantly, it will allow far more accurate targeting of suggestions to specific bacteria rather than trying to handle everybody. In other words, we are looking at a specific subset of people. For example, probably slightly jaded, but we are looking at a subset of people who ride Harley Davidson's motorcycle, have long beards, leather jackets, belong to a biker's club, versus everybody in the population. We could apply everything to the population, or we could try policing the biker's club. Filtering by symptoms allows us to focus on the biker's club rather than everybody in the population.